Hi, this is Aaron. I originally gave this talk in Japanese, but the organizers wanted it to be in English. So today I'm going to be interpreting myself, and I've never done that before. So let's see how it goes.
こんにちは。今日は
Hi everyone.
メモリを使おうと
Today I'm going to be talking about reducing memory by using more memory.
しかし主な内
but
容は Ruby の GC
Most of the talk is going to be about concurrent compaction development in Ruby.
このタイトルの方がいいと思ったので
But I thought this name was better, so I used it.
必ず後で
But I promise that I'll be talking about reducing memory in
ちょ
Ruby.
っと待ってください。
Just a minute.
前に話したことではありません。
This is not the same presentation I've given
私は
before.
アーロンと申します。
My name is Aaron.
上では私はこの人として
On the internet, I am known as
今
Tenderlove.
年私は幸運にも Shopify という
This year, I was really lucky to change jobs, and I started working at a company called Shopify. Currently, I'm working as a full-time Ruby developer at Shopify. In other words, like every day I'm doing Ruby development. And today I want to tell you what I've been talking about, or what I've been developing at work so far. In Ruby 2.7, I introduced a new functionality called GC Compact. This feature allows us to save memory by filling in space in our heap and eliminating fragmentation.
実現となりました。これは DOS に実装させている
This is the defrag utility in DOS, and it's a utility where DOS cleans up the hard drive, cleans up fragmentation in the hard drive, and the compaction functionality is essentially the same. It's just cleaning up memory instead of space on your hard drive.
このプログラムは Compaction の効果を
This program
まず
demonstrates the effectiveness of compaction. It loads a Rails application, then runs the GC to remove garbage, then compacts the heap to remove space. If we make a graph of the heap, the graph will look something like this. This graph is what the layout looks like before the compactor runs. Green and black dots are living objects, and white dots are free space. After compaction, the heap looks something like this. Green and black dots are regular objects. Red objects are objects that couldn't be moved, or red dots are objects that couldn't be moved. In this graph, it's hard to see, but in this graph, it's more narrow, and that means that we're actually consuming less memory. But before we dive into my current work, I want to cover what the existing algorithm is. Compaction process has two steps. First, it moves the objects around, and then it updates all the references. Let's look at the compaction process in more detail. Imagine there is a memory layout like this. The blue objects, or the blue squares, represent live Ruby objects, where white represents empty slots, yellow represents forwarding addresses. The compaction process requires two pointers, one at the beginning of the heap and one at the end. One is called the free pointer, the other is called the scan pointer. The free pointer scans right until it finds a free slot. The scan pointer moves left until it finds a filled
そ
slot.
してスロットを交換し、転送アドレスを書き込みます。
Then it swaps the slots and leaves a forwarding address.
が今3番目のアドレスに
What was in slot 9 is now in slot 3.
次に両方のポインターが出会うまでこのプロセスを繰り返します。
This process then repeats until both pointers meet.
オブジェクトの移動プロセスが終了します。
When the pointers meet, the object movement process is finished.
これは同じヒープのレイアウトです。
Here is the same heap layout.
おそらくあるオブジェクト同士はこのようなお互い
Before compaction, maybe some of the objects have references to each other like
オブジェクトが移動
this.
するとこの参照は正しくなくなりません。
But when the objects get moved around, the references will become bad.
はこのようになります。参照が悪くなったので、
After the objects have moved, the heap looks like this. The references have become bad, so we need to update all the references. To do this, we simply iterate over the heap, check the reference, then update it.
参照を確認して更新します。この場合、オブジェクト1は7を参照しています。
In this case, object 1 references object 7.
やったオブジェクトは4に移動したので参照を更新します。
But the object that was at 7 is now at 4, so we update the reference.
2を指していますが、
The next object 2 is pointing at 6, but 6 moved to 5, so we update the reference.
プロセスを繰り返して全部のオブジェクトの参照を見て更新します。
We repeat this process for every object in the heap and then update their
転送ア
references.
ドレスを消し、コンパクションは終わりました。
When this is done, we can clear out the forwarding addresses and compaction is
コンパク
complete.
ションに対しての私の目的について話します。まずメモリ量を削減する。
I want to talk about my goals for
重
compaction.
要なゴールです。
I want it to save memory. This is probably the most important goal.
知らない間にコンパクションが自動的に
I want it to be automatic. So in other words, I don't want developers to know it's happening.
的な勝利です。
It should be
他の勝利と
concurrent.
同時に実行され、
In other words, it can happen at the same time as any other process or any other processing.
ゴールについて話しましょ
And also, it should be fast. So let's discuss each goal. First is saving
う。
memory.
前と後のヒープを比べられます。
This is what the heap looks like before and after compaction. The number of objects is the same, but the compaction or the compacted heap is more narrow, meaning it uses less memory.
メモリ量が減ったという意味です。その後、ヒープにスペースがなくなり、オブジェクトが詰められるので、コピーオンライトの効果
Since all the objects are packed together much better, copy on write performance is improved.
は達成したと言えると思います。
So I think we can say the first goal is met. We do save memory, so let's take a look at the next
コ
goal.
ンパクターの自動化です。
That's making the compactor automatic.
必要なしに自動的に
Ruby developers shouldn't need to know that
でも
it's running or that it can run automatically. They shouldn't need to know about the compactor.
特別の機能
But today, you have to specially call GC compact in order for it to run. So, for example, we use it like this. First, it loads the Rails application, then it compacts the heap, and then it forks the web server. We have to call GC compact ourselves, so this is not automatic. We have to call GC compact, so this is clearly not automatic. So this goal is not met. Next, let's look at concurrency. Since we have to call GC compact ourselves, we already know that the compactor is not concurrent.
コンパクションアルゴリズムにおける一つの実装問題について
But I want to talk about one implementation problem with the current compaction algorithm. I call it the empty slot problem.
オブジェクトを移動する場合、空いているスロットのみ使用できます。
When objects are moved, the destination slot must be empty.
がこのために
This doesn't sound like a problem, but it means that GC steps must happen in a certain order.
前に話したが、Compaction Process には
As I said earlier, the compaction process has two steps. First is moving objects. Second is updating references. But since we can only move objects into empty slots, it means that the sweep step must happen before compaction can start.
スイープステップが終了しなくてはなりません。もちろんマークステップは
And of course, this means that the mark step has to happen before the sweep step.
空いているスロットの状況はコンパクションアルゴリズムが他の処理と同時に実行できない理由の一つです。
This empty slot requirement is one reason why we can't run the compaction algorithm concurrently with other processes. So we have to call GC compact ourselves, and the GC steps require a certain order. So we can say this is definitely not concurrent. Finally, speed is a relative issue. Maybe the compactor is fast, but since it can't be executed concurrently, we can't really talk about speed. In other words, we need to make the compactor concurrent before we can talk about speed. Making the compactor automatic and fast both depend on making it concurrent, so this is the problem I would like to talk about today. But when we say concurrent, what are we running concurrently with? Ideally, it would be best if it's running concurrently with your Ruby code. This way we can reduce the amount of time that your program pauses, but this is too hard for the first try. And I don't like doing hard things, so I wanted to start with something easier. Instead of making it concurrent with Ruby code, we'll start by making it concurrent with the sweep step. For the first implementation, we'll change the move step to be concurrent with the sweep step. So instead of a process like this, we have a process like this. We can make the sweep and object movement happen at the same time. Let's take a look at the sweep process and then talk about integrating the move process. I'm not going to explain the marking step, but after the marking step, any objects that we keep will be marked, and any objects that we collect will not be marked. The sweep process looks at each object. If the object is marked, it moves to the next one. If the object isn't marked, it will free the object. Then we repeat this process for all of the objects in the heap. What am I doing?
Yay! そしてスイープと移動のステップをつながり方を見ましょう。
Okay, so let's take a look at how to combine the sweep and move process.
動き方はコンパクトのフリーポインターに似ているから。
The sweep pointer looks very similar to the free pointer, so we should be able to combine these processes. First, let's add a scan pointer, just like we had in the compactor.
トは消した後でスイープスキャンポインターが移動できるオブジェクトを探します。
The sweep step remains the same, but after an object is freed, the scan pointer searches for an object, then it moves the object and leaves a forwarding address. We repeat this process until the sweep pointer and scan pointer meet. When they meet, we temporarily stop the sweep step.
スイープが止めているときにコンパクトと同じように参照を更新します。
While the sweep step is paused, then we're going to update all of the references just like a normal compaction process. 1 pointed to 6, but 6 moved to 5, 2 pointed to 7, but 7 moved to 4, and then we repeat this process as normal.
参照の更新が終わったからスイープは普通に続きます。
When the reference updating is finished, then the sweep step just continues as normal.
自然に自動的に転送アドレスを消します。
What's really nice about this is that the sweep step naturally and automatically removes all of the forwarding addresses for us. And now compaction is complete. So I implemented all of this, and all the CI tests pass. This is a PR. The build on GitHub was working, so I thought everything was fine, and then I merged the patch. But after I committed the patch, build started failing, so I reverted the patch.
しかし何が起こったのでしょうか。
But
アルゴリズムは正しいと思
what
った
happened?
けど、なぜビルドが失敗するのでしょうか。
The algorithm was correct, but what was the problem? It took me a while to figure out, but the bug is something like this. Here we have 3 classes, A, B, and C. Internally, Ruby tracks the class parents and class children like this. The child has a reference to the parent, and the parent has references to the children.
消される場合、GC が C を解放するときに C の参照
if class C is deleted, then when the GC frees class C, C's references must be removed from A. Then C can be freed. This means that during the GC sweep phase, the C class must access the memory of the A class. Let's look at the same process, but from the perspective of the garbage collector. The sweep pointer finds the C class. The C class isn't marked, so we need to free it. C must be removed from A's list, so it reads A's memory and deletes itself. Then the GC removes the C class itself. Let's look at the same process, but when compaction happens. The process for sweep and compact is about the same. But when it's time to sweep the C class, the A class is moved. The C class is pointing at the forwarding address instead of class A, so it'll try to read it tries to read the memory at that location. But it's a forwarding pointer, and since the memory is wrong, the program will crash. We can see from the crash that the class isn't a class, but it's a forwarding address. So what do we do about this problem?
想定していました。
Up to this point, I assumed that when an object was freed, it would only free its own memory. I didn't imagine that it would read a different object's memory. When an object is freed, should it be able to read other references?
フリーのファンクションに制限を作りたかった。でも他に同じ問題がある。
Of course, I'd really like to put restrictions on what the free function can do.
そのコードを
But I
壊さな
can't
いためには他の道を探さなくてはなりません。
I can't break existing code. So there must be a different way that we can fix this.
修正するために私が選んだ方法はリードバリアです。
In order to fix this problem, I decided to introduce read
リードバ
barriers.
リアは単に何かが何かを読もうとすると
But what are read
実行
barriers?
するファンクションです。
Read barriers are just functions that are called when something is about to be read. Let's look at a concrete example.
インスタンス変数が
This is a very simple example of a read barrier. When an instance variable is read, it executes a block. The read barrier allows us to take an action anytime something is read. If a moved object is going to be read, then we can use the read barrier to move the object back into place. In the case of our classes, if class C tries to read class A, the read barrier executes, and the read barrier can move A back to the right place. Unfortunately, read barriers have a few problems. First, they're complicated. Here's a very simple program. Let's find all the spots where a read barrier might need to execute. Of course, we need to add one when instance variables are read. We also need to add one when initialize is defined because the class itself might have moved. We need one when the instance variable is written because the foo class might have moved, the foo instance might have moved. And then we have to add it in all these different places, and this is just way too complicated, and I don't want to do it. Even if we had reburied all those places, it can slow our program down. This type of read barrier is treating our program as a type of graph. It protects the integrity of the edges of the graph. So if an instance variable moves, when the reference is read, the read barrier can execute and fix a reference. This type of technology is extremely powerful, but implementing it is very difficult, and it can slow down the program. I really like writing easy programs, so let's find an easier way to solve this. I chose to use the mprotect system call. This function allows us to change the permissions on a region of memory. We can mark the memory as no access. So if any code tries to read that memory, an exception occurs, and we can handle the exception. Let's see how this can fix our bug, and then let's talk about mprotect itself. This works the same as the previous algorithm, but after we move an object, we change protection on that location of memory to have no access. And each time we need to move an object, we remove the protection. Then after an object is moved, we add protection again. In this case, when the C class tries to read address 9, it's protected and an exception occurs. The exception handler removes the protection and then moves all the objects back.
スイープステップを普通に絶行できます。
Finally, the sweep step can continue as usual.
でも mprotect はパーフェクトではありません。
But mprotect is not perfect. It has some problems,
環境でしか使えません。
and you can only use it under certain conditions.
保護されたメモリ領域のアドレスは 4KB に一致しなければなりません。
Protected regions of memory must have addresses aligned at 4 kilobytes and must be multiples of 4 kilobytes.
mprotect の状況はメモリ領域のアドレスはの 4KB の倍数で、
To say it again,
領域のサイズも 4KB
to reiterate, the address of the memory must be a multiple of 4 kilobytes, and the size of the memory must also be a multiple of 4 kilobytes.
します。
This is the code. This is the code in Ruby where object memory regions are allocated. The memory region address alignment is in the heap page align constant. The value of heap page align is 1 shifted left 14 bits. 1 shifted left is 14 is 16,384, and 16,384 is a multiple of 4 kilobytes. So we verified the address as a multiple of 4 kilobytes, but how about the size? The size of the memory region is heap page size. Heap page size is heap page alignment minus required size by malloc. Required size by malloc is size of size t times 5. If we do all the calculations, unfortunately, heap page size is not a multiple of 4 kilobytes. Unfortunately, since the size of a page is not a multiple of 4 kilobytes, we can't use mprotect. But this made me start to think, like, what if we allocated exactly 16 kilobytes? If we allocated exactly 16 kilobytes, then I can use mprotect. In addition, required size by malloc is the same size as one Ruby object. If we allocate 16 kilobytes, then each Ruby page can actually store one more object. So I sent a patch to Ruby to extend heap pages to be exactly 16 kilobytes. In order to test the patch, I used RDoc documentation generation as a benchmark. I generated RDoc documentation and recorded the process size. This is a graph of the memory usage over time. The x-axis is time and the y-axis is memory usage. The red line is the master branch and the blue line is the branch with my patch job applied. I ran the benchmark 50 times. From the graph, we can see that with the patch applied, running RDoc actually uses less memory. This graph is a graph of the maximum amount of memory. This is a graph of the maximum used memory. The left side is the master branch and the right side is the feature branch. From this, we can see that the median memory usage on jemalloc is usually lower. What these graphs are saying is that when we request more memory, we actually use less. So why is this? jemalloc uses fixed size blocks, and 16 kilobytes is one of the block sizes. Allocating nearly 16 kilobytes will reserve an entire block, but the 40 bytes at the end will be wasted. So we store Ruby objects in this blue block, but the remaining 40 bytes is unused. However, if we allocate exactly 16 kilobytes, the entire block is used. If we allocate this convenient size, it means that we can use memory more efficiently and reduce the overall memory usage. And this is why I call the talk Reducing Memory by Using More. Anyway, this is the whole patch. The important part is here. Heap page size is now the same as heap page align. Now the page addresses are multiples of 4 kilobytes and the size is a multiple of 4 kilobytes, so we can use mprotect. I made a pull request here that uses mprotect to implement a read barrier and combines the compact and sweep. The PR is here. The read barrier works very well, except that it's way too slow. This benchmark compares the speed of the compactor with a read barrier and without a read barrier. The version with a read barrier is way slower. It's about 4.5 times slower. I don't think that's very good. So now the compactor is concurrent, but it got 4.5 times slower. So I'm not sure that I can say that it is fast. Currently, I'm working on speeding up the compaction process. According to the profiles, the bottleneck is mprotect. Right now, the compactor makes a lot of calls to mprotect, and my current idea is to reduce the number of calls to mprotect. I think there are various ways to do this, but I just haven't been able to try them yet. Okay, I think it's time to wrap up. So far, this project might look like some kind of failure because I made compaction so slow. But actually, the progress I've made so far has given me lots of hope and made me very excited. Even though the code is slow, I was able to prove that we can effectively implement and use a read barrier. Adding a read barrier is required for executing concurrently with a Ruby program. Proving it's possible to add a read barrier is an important achievement. I was able to add a read barrier, and now all I need to do is make it fast. Thank you all so much. I hope that I can see you in person at RubyKaigi 2021. Oh my god, that was hard. Hey Gorby, you're a good cat. Read